Now let us consider an active medium from which the transition is taking place from one level to the other. So suppose we consider first the case of stimulated emission. Okay, stimulated absorption. Let us consider the case of stimulated absorption first. Okay, so here if N1 be the number of atoms per unit volume present in the energy state E1, number of atoms per unit volume present in the energy state E1. Okay, that is what we call N1, and if N2 be the number of atoms per unit volume in energy state E2. Okay, then, well, if a radiation at a frequency corresponding to the energy difference E2 minus E1 of the two energy states fall on the atomic system, then when stimulated absorption is taking place, what can we say? The probability of the occurrence, suppose if I call this as P12, the rate of transition of atoms from state 1 to state 2. So suppose if I draw this diagram over here, E1 and E2. Okay, so then the probability of transition that takes place of the atom from this state to this state, this is your initial state and this is your final state. Okay, so the probability of transition that takes place, if I call this as P12, because this is happening from state 1 to state 2, if I call this as P12, P12 will be proportional to N1, because transition is taking place from the lower state to the upper state. Okay, the number of atoms present in state E1, this will be proportional to P12 will be proportional to the energy density U nu. If I call this the energy density of radiation of frequency nu, U nu is the energy density of radiation of frequency nu. If I call that as U nu, where what is nu? Nu is the frequency. It is the difference between the energy E2 minus E1 by H. Okay, then P12 will be proportional to U nu. Alright, which is the energy density of the radiation. Okay, now what is U nu? U nu will be equal to NH nu. H nu is the energy, alright, and N is the number of photons of frequency nu per unit volume. So here we define N as number of photons per of frequency nu per unit volume. Number of photons of frequency nu per unit volume, and H is the Planck's constant. So the number of atoms undergoing absorption per unit time per unit volume from the energy state E1 to E2, okay, which I am calling as P12, which is actually it is it is actually your rate of transition of atom from state 1 to state 2. Okay, so that will be, because it's proportional to n1, it is proportional to u nu, so that will be equal to, well, B12, okay, n1 u nu, isn't it? Sorry, u nu, I have put that as suffix. B12 n1 into nu u nu. Now what is B12? B12 is the constant of proportionality, which is known as Einstein's coefficient for stimulated absorption. Constant of proportionality. This is constant of proportionality. It is also known as Einstein's coefficient of stimulated absorption, or Einstein's coefficient of stimulated absorption. Einstein's coefficient of stimulated absorption. And it depends on what? It will depend on the properties of the energy levels E1 and E2, depending on E1 and E2. Okay, so now after the stimulated emission, we have, well, downward transition by two methods. What are the two methods that we discussed now? One is the, after the stimulated absorption, we have downward transition by two methods. What are the two methods? One is stimulated emission and another is spontaneous emission. We have discussed it just now, isn't it? So how do we define stimulated emission now? As I told you, the same probability if we now discuss for the radiation which is incident on the atom, which is stimulated by photon of frequency h nu, okay, h nu 12, same frequency, then it will depend on what? This stimulated emission. So stimulated emission is taking place, suppose say like this, of an atom now which is in the energy level E2, and it's going to come back to E1, okay, due to a photon which is acting on it of energy h nu 12, if you call it h nu 12, okay, and this emission will result in two photons, h nu 12 and h nu 12, after the emission process has taken place. Why? Because this photon acted as a stimulant. So this will, the probability now will be P21. I'll call this probability as P21. Okay, P21 will be proportional to the energy density u nu at frequency nu, which is equal to n h nu, okay, and the number of atoms that are present in the energy level E2. Okay, if that number is n2, suppose say, so P21 will be equal to B21 n2 u nu. Same thing, where n2 is the number of atoms in the energy level 2. Okay, all right. So what is B21? Well, B21 is the proportionality constant, which is Einstein's coefficient for stimulated emission. This is Einstein's coefficient for stimulated emission. What remains is now spontaneous emission. Okay, what remains now is spontaneous emission. So for spontaneous emission, what will you have? The same frequency, okay, which is emitted spontaneously from this level. It is not stimulated by the energy density. So if you call this emission not as P21 or P12, but you call it as say P prime, okay, 21, the spontaneous emission. On what will it depend? It will not depend on the energy density anymore. It will depend only on the number of atoms present in the energy level E2. So if that number is N2, then P21, if I call it as prime, it will be equal to A21N2. Okay, so this is Einstein's coefficient for stimulated absorption. Stimulated absorption. Is that okay? So, well, if you have understood this, then, well, what can you say? All we can say is that P12, from the principle of conservation at thermal equilibrium between the atomic system and the radiation field, the number of upward transition must be equal to the number of downward transition. So at thermal equilibrium, P12 should be equal to P21 plus P21 prime. Okay, so let us start our next video with this discussion. That means what happens at thermal equilibrium. At thermal equilibrium, obviously the amount that is absorbed should be equal to the amount emitted. So absorption coefficient should be equal to the sum of the emission coefficients. Okay, so let's stop over here to describe our last video.